Let's really start to dig into organic chemistry. Now we're going to start with a section of organic chemistry called alkanes. Now alkanes are generally the most simple form of an organic compound that we can look at. So an alkane is a carbon-to-carbon bond, and those carbon-to-carbon bonds are single bonds. So what that means is that we have a compound that has carbon bonded to a carbon, bonded to a carbon, bonded to a carbon. Okay, so all that means is that these bonds are single bonds, or in other words, those two carbon atoms are sharing electrons. Now, again, we're talking about these compounds that are hydrocarbons. So we don't just have carbon in these compounds, we also have hydrogen in these compounds. So we have a general formula where it's Cn, and N can be any digit, and H, which is 2N plus 2. So we'll take a look at what that means. Okay, so essentially, these alkanes, when we call them saturated hydrocarbons, what that means is they are saturated or full, okay, saturated means full, of hydrogens. So we know from chemistry 20 that a carbon atom has 4 bonding electrons, which means that carbon can form a possible total of 4 bonds. Okay, so what we see is if we have a carbon chain, which is what we call this here, okay, we have a carbon bonded to a carbon, and then each of the other bonds that can potentially be around each carbon is full of a hydrogen. So any line that I've just added here is a new bond that is all saturated or full with hydrogens. Now obviously we have to have a certain amount of electrons shared between our carbon atoms, but every other bond is filled by a hydrogen. So this is a saturated hydrocarbon. Now to get back to our formula here, what we see is our general formula, especially for the example that I just wrote down here, is C to the N, which is how many C's I have. So let's just write this down. I have C, and how many C's do I have? I have 1, 2, 3, 4 C's. So I would write this down as C4, okay? And H, my H is 2N plus 2. So if I follow the math through, if N is 4, I have 2N, which is 2 times 4, plus 2. So I have 2 times 4, which is 8, plus 2, which is 10. So I should have a total of 10 hydrogens on my compound. So when I take a look, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I have C4H10. Now, we'll learn how to name molecules like this as we go through, but essentially you need to know the general structure of these carbon chains first. So naming alkanes. So what we've seen throughout chemistry, from chemistry in Science 10 all the way to here in Chemistry 30, we've had different naming systems and naming schemes, and that's all from our IUPAC. So that's the International Union of Pure and Applied Chemistry comes up with these naming systems for different compounds. Now, our organic naming system is slightly different. What you might remember is we have some prefixes that we've used, and in any sort of naming of a molecule, we have our 1, which was mono, 2, which was di, 3, which was tri, 4, which was tetra. Okay, and then 5, we had penta, 6, hexa, 7, hepta, I'm going to run out of room here, 8, octa, 9, nona, and 10, deca. Okay, so what we know so far is that we use these prefixes, and that's all fine and dandy. However, in organic chemistry, we actually see that there's some new prefixes for these organic compounds. Now, it's not saying that we can just throw these ones out the door. We still need to be aware of them and use them in this unit, but we are adding some new ones. Now, essentially, what these prefixes mean is it is finding the longest carbon chain. So these new prefixes that are in red in this chart here are our new prefixes, but it's only for that longest carbon chain. Now, meth is the prefix for one carbon in the chain. Eth is 2 carbons in the chain. Prop is 3 carbons in the chain. Bute is 4 carbons in the chain. And then pent, all the way through dec, are consistent with our previous prefixes. They're not really new. We just have a new one for 1 through 4. So these top 4 are the ones that we might need to have a new way of remembering our prefixes. Again, meth 1, eth 2, prop 3, bute 4. So those ones you may need to do a little bit of memorization to be familiar with those 4 prefixes. And again, these prefixes are referring to the length of the carbon chain. So what you'll notice is in my formula, in methane, I have 1 carbon. In ethane, I have 2. Propane, 3. Butane, 4. Pentane, 5. Hexane, 6, etc. Okay, so you'll notice that these refer to our carbons in our chain. Okay, that is very important as we continue through. So, let me actually just jump back, and I'm actually just going to draw some of these out. So if I look at my example of methane, I would literally just have a carbon with 4 hydrogens around it. Okay, with ethane, I would have 2 carbons with 6 hydrogens around it. Propane, 3 and 8, butane 4 and 10, okay, pentane 5 and 12. So as you go, you keep on adding, I'll just skip to butane here. I keep on adding my hydrogens and my carbons in a single line chain. Now, what you'll notice as I go through these notes here from this point forward is that when we're drawing structures, we should always include our hydrogens. This would be called a structural formula, okay? And that's proper notation for a structural formula to have all of our hydrogens written out like I've just added. However, what you'll notice in my notes is I kind of get lazy. I like to simplify it, and anytime that I draw a line, what that means is that at the end of the line, unless it's otherwise specified, it means that there's a hydrogen there. And it's just to simplify it a little bit, but if you see that, please don't get confused from this point forward. There would be a hydrogen attached to that line unless, like I said, is otherwise stated as a different element. So, structural isomers. Now, what is a structural isomer? It is a compound with the same molecular formula, but with a different actual physical structure. So we can look at how these things might differ. We might have some branches off a chain that change the overall physical structure, but the molecular formula of a compound could remain the same. Okay, so this we call, if there's a branch, we call that branch an alkyl branch. Okay, so essentially a structural isomer could be a branched isomer that has these alkyl branches off them. Now, when we go to name alkyl branches, we end them with a YL suffix. Again, we call it an alkyl branch, therefore we continue that YL suffix throughout our naming system. Okay, now some of this, again, it may not make sense until we see some examples, but we'll get to that in 1 second here. So definitely write down structural isomer as a definition. You will need to be very familiar with this for your diploma exam. They will, without doubt, have a question on structural isomers on that diploma. Okay, so if we go to draw some of these alkanes, okay, now they're all alkanes because they have all, again, remember an alkane is a carbon compound that has a single bond or single bonds. Okay, so in between our carbons are single bonds. Now when we go to draw these things out, if I draw pentane, I'm going to draw, again, the structural formula. I'm going to draw pent, meaning 5. So that means 5 carbons. 1, 2, 3, 4, 5 carbons in that carbon chain. And because it's a saturated hydrocarbon, or we have, I'm just going to put saturated beside, it is saturated with hydrogens, meaning that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens. Now, again, this is where I'm talking about if I leave my drawing like this, each of these ticky lines represents hydrogen. However, it is correct notation to, in fact, draw out all of my hydrogens. I do, however, find it takes up a little bit more space, and when I am limited to how I'm drawing here in this presentation, I like to keep things a little bit more simple than that, but I will have that there for you to see. Now, methylbutane. So bute is one of the new ones. Bute means 4. So if we look at what methylbutane means, well, meth again means 1. And you'll notice that we have this YL. So that this means that I have a methyl or an alkyl branch that is 1 carbon in length. Okay, so we have to be careful of our naming. This YL tells us that there's a branch, and this meth tells us how many carbons are in this branch, and then this bute tells us how many carbons are in what we call our parent chain. So I'm going to do this in a new color just so you can see the difference of my two molecules and my hydrogens don't get too crowded here. But if I draw butane, now I always start with my longest parent chain first, so bute meaning 4. And if I draw 4 carbons in a row like that, essentially that's my bute, okay? Now what it's saying is I've now accounted for my butane, but now I need to have my 1 carbon branch coming off some part of my chain. Now, the one trick with organic compounds is that we can have a bent chain. So if I go back to my pentane example, I could have drawn this chain of 5 carbons in a straight line, or I could have drawn it like this. 1, 2, 3. Actually, let's do 1, 2, 3, 4, 5. Now, however, even though this looks like a different molecule, it is in fact still pentane. I have 1, 2, 3, 4, 5 carbons in a row. Now, the reason why these two molecules are the same, okay, is because this branch is coming still off of the 3rd carbon. Now, the reason that is if we remember back to our what color should I do here? When we go back to remembering our shapes of molecules, when we have a molecule that has 4 bonds, or it's tetrahedral, we know that 2 of the bonds go into the plane of our page, essentially, and that 1 of the bonds is coming out towards us, and 1 of the bonds is going in towards the carbon. So if we have something like this, and let's just use an example with methane just because it's simple. Okay, it doesn't matter if we were to rotate this hydrogen up here to any one of these spaces because it's still the same molecule. It is still methane regardless of which angle that bond is coming at. Okay, so essentially because this is a 3-dimensional molecule, this molecule here and this molecule here are the exact same. There is just a twist at one of these angles, meaning that this is the identical molecule. So that becomes a little bit tricky. What it means is that when we look at branched molecules or branched isomers, we always have to think about the fact that we cannot add a branch to either one of our terminal carbons. So this guy here, okay, or this guy here, we can't simply add a branch there. We can't add our 1 carbon branch because all of a sudden that would turn it back into pentane. Now, since this is not pentane, we have methylbutane, we need to think of a location that we can plant this branch off of our parent chain, okay, or our tree trunk, that we will not get a bent pentane molecule. So when I do that, I know that I can plant my branch on either one of these two middle carbons. It doesn't matter, again, if I have it on this first carbon, it's essentially the same as putting it on my second carbon, because if I go look at my molecule from this direction, it's on the second carbon, and if I look at my molecule from this direction, it was on the second carbon as well. So regardless of if I were to flip my carbons or my molecule around, it's still coming off that second carbon, which we'll talk about a little bit again when we're naming it. So essentially what that tells me is my methyl group has to come off of one of my center carbons. I'm going to pick this one for simplicity's sake. Now, because it's a one carbon branch, I'm going to just draw that carbon out. Okay, so essentially I have my butane with my single carbon branch coming off of one of my middle carbons. That's what's important. Now when I go to write the rest of this compound out, I need to make sure that I know that this is a saturated hydrocarbon. In other words, we're saturated with hydrogens. And again, in this example, I'm not going to fill in all of these tickies with a hydrogen just for the sake of saving space. So in this question, I have so far written down 5 carbons, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So if I go back to my pentane, this was C5H12, and magically enough, this methyl butane is also C5H12. Again, remembering that each carbon can contain 4 bonds because it's a tetrahedral molecule. So each carbon, when we check it out, has 4 bonds, and we have our saturated hydrocarbon here. Now let's take a look at our last example here for a structural isomer. We're looking at dimethyl propane. So again, I see that I have my prop. Okay, my prop means 3. Now, whenever I see my propane or my butane or my pentane, that is what we call our parent chain. So I'm going to draw that down right away here. I know that it's prop, meaning that it's 3 carbons. Okay, so I have 3 carbons in a row. That is propane. Okay, now what I see is I have methyl, again, YL. Now my YL group tells me that it's a branch. I have a branch on this, and this meth tells me that there's a single carbon branch. But the interesting thing that we need to take a look at is this di. Like I said before, we can't disappear our other prefixes. We're using them simultaneously with this new naming system. So we have dimethyl propane. So what that tells me is I have 2 times my 1 carbon branches. So I have 1 carbon branches, but I have 2 of them. And then I have them coming off my 3 carbon parent chain. Okay, so what that tells me, again, I can't ever place a branch off of what we call our terminal carbons. I can't put it at the beginning or at the end because all of a sudden that would change my branch to be a longer branch than what I have. That then tells me that these 2 carbons must be attached to my center carbon. So I have a 1 carbon branch here, and in fact I have another single carbon branch down below. Now again, because this is a saturated hydrocarbon, I need to then fill all the rest of the spaces up with hydrogen. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, hunky-dory, look at that. We have C5H12. So again, we have the exact same molecular formula, okay, but we have very different structures. Pentane was all in a line, methyl butane was in a line with a single branch, and dimethyl propane was 3 carbons with 2 separate branches. Now notice with dimethyl propane, I could have called this carbon number 1, 2, 3, or I could have counted it from the other direction and gotten carbon 1, 2, and 3, which is fine. Either direction, again, it's based on a 3-dimensional orientation of this molecule, but again, we have the exact same molecular formula for all 3 examples, which is, in fact, structural isomers. Now, when it comes to organic chemistry and what we need to know in preparation for a diploma is there's actually 3 different ways of naming or drawing structures. So we have a structural, okay, and structural is the components that we've seen on the previous page there. We draw out essentially every atom and the bonds between the atoms. Okay, a condensed is a way of writing these things that is a little bit more simplified. We can look at just the atoms and their adjacent atoms that are bonded to those. And then the most simple is our line diagrams. They're my favorite. They're very simple and easy to draw, but they're maybe a little bit to interpret in the other way if you're looking at a drawing and trying to get the name of it. So let's go through our 3 examples that we saw on the previous page just so that we know what these look like already. Now I'm going to zoom in on this page here, so you're going to lose part of the slide, but just so I have enough room that I can fit all of these structures in on this one page. So starting out with our structural diagrams, I'm going to start with our pentane again, which is structural 1, 2, 3, 4, 5, and again, fill that guy up with hydrogens all the way around. So I should have a total of 12 hydrogens all the way around this guy here. So 5 carbons, 12 hydrogens. Okay, if I look at my methyl butane, again, I have my parent chain, bute, being 4. I have my hydrogens off of this guy, and I believe on our previous slide we put our methyl group here. So we have hydrogens coming off this guy, hydrogen here, hydrogen here. Again, we have C5H12. Okay, now if we look at dimethylpropane, which I'm going to have to squish in the bottom here. Okay, I'm going to kind of squish over in this corner. I have prop, meaning 3, so 1, 2, 3, plus my dimethyl, so I have 1 methyl group, and again we call this a methyl group. It's 1 carbon with 3 hydrogens, and we have 1 carbon with 3 hydrogens, and the remaining portion of our molecule is full of these hydrogen atoms that surround each carbon to fill up all of the remaining bonds. Now, as you might notice already just from my diagrams, these tend to get fairly cluttered and cramped, and sometimes you miss hydrogens, and there's so many things that you can mix up and mess up, and your examples will get clumped together. And that is again why I would prefer just to write this out. I know what's going on, and as long as we kind of have a little agreement here that this is a little bit easier to view than this guy, and that we know that each of these has hydrogens, then that's easy to go through the rest of this unit like that. Okay, so there's our structural formulas for these three molecules. So then let's look at condensed formulas. Our condensed formulas. Now, essentially what we do is for a condensed is we write down any sort of atoms that are attached and the adjacent atoms that are attached to that. So what I mean by that is we're going to take a look at each carbon individually and the hydrogens that are attached to that. So for pentane, what that would look like is I would have C, and around that carbon I have 1, 2, 3 H's, so I have CH3. Okay, and then I can either draw a little line here, or you can just write it right beside. I like to give myself a little bit of a space there. Okay, then with my next carbon, which is this guy here, I have 2 hydrogens, so then I would write CH2. Okay, then my next guy over, I have CH2 again. My next guy over, I again have CH2. So that's 1, 2, 3, 4 carbons. So my last carbon on the end, I have C again with 3 H's. So this is a condensed formula for pentane. Now, to even condense it down a little bit more, what we like to do as chemists, because quite frankly, we're lazy and we don't like to write out more letters than we need to, we can write out something like this. CH3 and then we can have CH2 in brackets. Now the CH2 in brackets, essentially I'm just going to count how many CH2s I have in a row. I have 1, 2, 3, meaning that I have CH2 to the third exponent, or I have 3 of those guys inside, and then another CH3. Okay, so this is the most condensed formula that we can get when we're still using our letters. So we can do anything like this when we're drawing our condensed line structure, or condensed structural formulas out, pardon me. Okay, let's take a look at our methylbutane. So again, if I go through and I count my hydrogens around each carbon, I have CH3. And then I have this carbon here is actually only bonded to one hydrogen. So I have CH, and then I have CH2, and then I have CH3. But notice this guy isn't happy yet. He only has 1, 2, 3 bonds, so we can't forget our alkyl group that has a CH3. Again, this is the most condensed that this formula can get because there's nothing I can put in brackets to simplify. Okay, I can't put CH3s in brackets because that doesn't show me their general location of the CH3s, which I need to have. Putting the CH2 in my previous example in brackets told me that there's 3 CH2s in a row. But because I have 3 CH3s in different locations on this guy here, I can't do the same thing for this. Now for our last example, again, I have CH3, C, no H's around that guy, CH3, something like that. Again, you'll notice that these condensed structural formulas are a lot more simple to look at than these structural formulas. It's a little bit more tidy, a little bit nicer to look at than this kind of mess that we have on the left. However, like I said, you do need to know and be familiar with all 3 types of these drawings for your exam and your diploma. Okay, so let's take a look at these line diagrams. Now, line diagrams are, like I said, I'm a little bit biased, but they're my favorite. And essentially a line diagram is a diagram that at any point that we have a point or a pivot or a change in direction of a line, okay, we have an atom, a carbon atom present. So what I mean is anytime that we have a point or a pivot in a line, we have a carbon atom. So for pentane, I would start and I have 1, 2, 3, 4, 5. Okay, so that kind of got messy there. Let me just redraw that whole thing just to be simple. 1, 2, 3, 4, 5. And again, I'm going to point out the carbons. This, as I have it, is perfect line diagram, but if I point out the carbons, and you may want to do this as you're getting familiar with our line diagrams, just so you can keep track of your carbons, because it's easy to mix up where your carbons are. Okay, I will draw a little dot showing each carbon. So there's 1, 2, 3, 4, 5. Now, because at this point we're getting to be experts in organic chemistry, there's no need to indicate where your hydrogen atoms exist in this molecule. Because we assume it's a saturated hydrocarbon, we know that there's 3 here, there's 2 up and down, 2 up and down, again up and down, and then 3 at the end. So this is the most simple form that we can draw our pentane. Now if we take a look at methylbutane, again I draw any time that there's a point or a change in direction or a pivot of that line, it represents a carbon atom. So I have 1, 2, 3, 4, which is butane. So again, that's 1, 2, 3, 4, which is butane. And then I have a methyl group. Again, it doesn't matter if I'm coming off of this carbon or this carbon, but I have to represent that carbon by an end of a line. So I have it there. And again, if you don't need to draw the dots, it's better to not draw the dots because it looks like you're trying to maybe draw a constellation rather than an organic compound. But again, the dots do help you understand where those carbon atoms are. Again, no need to draw in our hydrogens. Let's take a look at our dimethyl pentane. So we have 1, 2, 3, just kind of looks like an upside down V so far. And because we have dimethyl pentane, we have a carbon up at the top and a carbon down at the bottom. So what we actually see is there's 1, 2, 3, 4, 5 carbons, and again, all full of hydrogens. So these are, it kind of looks like you're maybe trying to draw a new language with your line diagrams. However, they do simplify what you're viewing and what you're looking at. If as we get going through this unit, you'll find that you'll start to kind of lean towards the things that take less time to jot down. Again, please be familiar with all 3 of these. And if you really need to dig in and pause this video at this point to make sure you're understanding how to do them, definitely take a minute to pause right now before we continue on. Now, naming, if you want the steps in verbal lingo, the way that we name any sort of branched alkane or any alkane period is to step 1, identify the longest continuous chain. Now that's very important. We need to find that longest chain of carbon atoms. Okay, we number the carbon atoms starting from the end closest to the branches. So what that means is when we do this, we want the lowest possible number when we're naming these branches, because we actually do need to start identifying the location of our branches, which I'll get to in our examples. Okay, so we want lowest numbers and we want the longest continuous chain. Okay, we need to identify any branches and their location number on that parent chain. Okay, we need to write down our IUPAC name in this format. Okay, the number of the location, which is the number of your branch, okay, which we'll get to in a minute, then followed by the branch name, so methyl, propyl, butyl, whatever it might be, and then your parent chain, which is your hexane, heptane, propane, anything like that. Okay, now one thing that you need to remember, because IUPAC has very, very specific rules when we're naming these things, is we write the name of the alkane, but we list the branches in alphabetical order. Okay, so we ignore the di and tri prefixes on those, but when we're naming our branch names, okay, we would name ethyl, okay, which is 2 carbons. We would name ethyl before methyl. Okay, again, because we write it in alphabetical order, E before M. So that's the rules to remember. And again, I would definitely jot these down. If you need to simplify these in a way that is a little bit more condensed, please do that. But definitely know these steps, because you will be tested on these naming schemes, and you'll definitely see it on the diploma. So you got to be pretty familiar with this as we go through. So when we take a look at some examples here, I'm going to show you how I would go about solving these. The first one is a little bit more simple than our second one, and I'm going to show you how I go about them, and then you can figure out your own way if you find a way that's consistent and good. So if I look at my first example here, I need to find my longest parent chain. Now that's my first step. I generally, if I'm given an example like this, I generally like to draw a line all the way through my molecule to get my longest parent chain. So I can either have this chain here, or I can actually have this chain here and it is the exact same length. So I have 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Okay, now just because my brain works in a way that is sort of the simplest way to view these things, okay, I'm going to label it this direction. I'm going to say 1, 2, 3, 4, 5. There's my longest parent chain. Now the second step is to number our carbons based on the lowest number being closest to our branches. So again, if you were to picture this as a pencil, okay, and if I have the end of my pencil like this and your eraser down here, okay, picture this as an eraser. I know it's a really terrible drawing. Okay, so there's my pencil. Now, if I was to look at my pencil in this direction, say with the end of the pencil pointing to the right, okay, essentially I would have carbons number 1, 2, 3, 4, and 5. Well, if I simply just flip my pencil, so all of a sudden it has the tip of this pencil pointing this way to the left, what I would notice is that it appears that this side of my carbon chain is now closer to the left side. So I don't always number from left to right. I number based on my smallest number of branches, because first of all, it's the most simple way to do this, but it also doesn't matter whether I number it as a 4 or a 1, because really it's just you have to picture this as a 3-dimensional orientation. So again, I'm going to number these carbons based on having my lowest number to my branch that I have there. So what I'm going to do is I'm going to number them this way: 1, 2, 3, 4, and 5. So that's my longest parent chain that I have present. Now, once I've done that, I like to jot down the fact that I have my longest parent chain, and I like to write it down because I know it already. I know that it is pentane, and that's not going to change regardless of my branches. Now, the other thing I need to note is that on my second carbon, I have a single carbon branch. So this means that I have a methyl group. And I only have one methyl group, okay? And it's coming off my second carbon. So how I would label this is I would write down that I have 2, which means that it's coming off my second carbon. Okay, this 2 matches my purple 2 there. And I have 2, and actually I'll circle this in orange. Oops, in orange here. So you know 2. So I have 2 methyl pentane. Okay, so that is how I go about naming that compound. Okay, so again, find our longest parent chain, number our carbons with our branches with the smallest numbers, identify our branches, and then write them down with the location, the branch type, and our parent chain. Let's take a look at this next guy here. Okay, so I see that my longest parent chain, and what I would suggest right now is pause the video, try and do this on your own, really try and figure it out instead of me just giving you the answer, because that's going to be the best way you learn how to do these, okay? So my longest chain I see is this guy here. Now I start at this carbon, I go down, and notice that this branch here isn't really a branch. It is still part of my longest parent chain. So this whole big zigzag structure here is our longest parent chain. Now I'm going to circle my groups again because I know that I have 2 groups here. Because these aren't connected, okay, now because they're each being branched off a different carbon off of the parent chain, instead of having a group that we would call an ethyl group, meaning a 2-carbon group, we have 2 methyl groups. Again, notice that it's coming off of 2 separate carbons. If you were to have both of the carbons connected, coming off of a single carbon, you would in fact have an ethyl group, but not in this case. So when I number this, I'm going to number with the edge of my carbon having the lowest coefficient. So if I write this down from left to right, I get 1, 2, 3, 4, 5, and 6. If I was to number it from my other direction, I would have 1, 2, 3, 4, and 5. So what I would see is if I compare those values, I want my branches to have the lowest numbers. So if I have 2 and 3, that is less than 4 and 5. So I'm going to keep my numbering from the left to the right. Okay, so I name these, and I have groups coming off of 2 and 3, and these are both methyl. Again, be careful, this isn't an ethyl group, we have 2 methyl groups. So the way that I would write this, because they're coming off 2 separate carbons, I would write that I have 2, 3, and then I have di, because there's 2 times these methyl groups, dimethyl, and my longest parent chain is hex, meaning 6, hexane. Okay, so I have 2, 3 dimethylhexane. Again, please be careful when you're naming these because it can be easy to come up with a new magical name. Okay, so drawing branched alkane structural formulas. Again, we'll attach all branches to their numbered locations on the parent chains, add enough hydrogen atoms to show that each carbon has 4 single bonds. We've kind of taken a look at this drawing of alkanes and branched alkanes, but we're going to take another look just in case. So in my first example here, and I'm going to draw these because I don't have a lot of room here. I'm going to draw these and then erase my drawings and start with the next example because I don't have enough room to fit them all in here. So my first one, okay, I will do this in purple. 3-ethyl 2,4-dimethylpentane. Okay, a few things to notice. Pentane is my parent chain. All right, now a few other things that I noticed here that might be a little weird, okay, is that I have 3-ethyl. Notice ethyl is before methyl. This di doesn't matter, okay? 3 is before methyl because 3-ethyl is before 2,4-dimethyl because it's alphabetical. So I have 3-ethyl and I have 2 and 4-dimethylpentane. So I see that I have 1 ethyl group and 2, okay, dimethyl groups, or I have 2 methyl groups. So when I go and draw this out, I'm going to start with my parent chain. It seems the most simple to me. And I can draw that out first. So I have pentane. 1, 2, 3, 4, 5. Okay, I have 2,4-dimethyl. Now I'm going to start with methyl. Again, remember, meth is one of those single carbon branches. And if I number this just for simplicity's sake, because I'm drawing, I can make it whichever orientation I want. I'm going to number it from left to right. 1, 2, 3, 4, and 5. Okay, so I have 2 and I have 4 dimethyl. Okay, so I have 2 of these groups coming off of this. Okay, and I have 3-ethyl. So off this carbon, I have eth, meaning it's a 2-carbon branch, okay, coming off of that 3rd carbon. Now the remaining portion of this is filled in with hydrogens. Okay, so this is the structural formula. If I'm to simplify this into my condensed formula, I would get that CH3 with CH. Again, it doesn't matter, by the way, which direction I have these carbon branches coming off of this molecule, because, again, this exists in 3 dimensions. This carbon can rotate in any point around this carbon atom. Same with this one, can rotate any way around these carbon atoms. They're totally rotationally sound in either way. Now, the reason that I draw them staggered like this is because simply I don't like it all cluttered in one spot, so I like to space it out. It gives me a little bit more room to write. Honestly, that's the only reason why. So again, coming off my 3rd carbon, I have CH2 and then a CH3. Okay, that is my ethyl group. And then I have CH again with my CH3. And then I have CH3 at the end. So that's my condensed line, or my condensed structural formula, pardon me. And if I was to draw my line diagram out for this guy here, I start with my pentane, 1, 2, 3, 4, 5. Looks like a giant M. Okay, and then I have 1, 2. So this is my 2nd carbon where I have a methyl group. So I have 1, 2, 3, 4. There's my dimethyl. And then my 3-ethyl, 1, 2, 3, comes off like that. So if I count my carbons, I have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 in both of those examples, and I have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so we can count all of our atoms and we are consistent with all of our diagrams. Okay, let's take a look at our next example here, which is 2,3,4-trimethylpentane. So let's just erase this and we'll take a look at that next example. Again, if you needed to just go back there and pause the video and make sure you have all 3 diagrams jotted down, do that. Just take a little second, jog back a little bit and write all of those down. Okay, I think we got rid of most of that off that page here. So let's take a look at 2,3,4. Again, we have 2,3,4. Tri, meaning we have 3 methyl groups, and pentane is, again, our longest parent chain. So if I was to draw that out, I'm going to just jot it down here. 1, 2, 3, 4, and 5, and I have 2, 3, 4 trimethyl pentane. Again, if I fill these in with some hydrogens, that's what I get there. So 2, 3, 4 trimethyl pentane. If I was to do this as a condensed structural formula, we'll get CH3 okay, and my line diagram, pentane, 1, 2, 3, 4, 5, okay, and I have trimethyl, something like that. Okay, so that is what I would get for my second example. Again, if you need to go through, count your hydrogens a little bit more carefully than I did, take your time, please do that. I'm just wanting to get through some more of these examples as we go through. Okay. So let's try the next example. Again, it didn't matter which direction I numbered this carbon atom or this carbon chain because I had 2, 3, 4. It wouldn't matter if I numbered it from left to right or right to left. It would give me the same exact answer. Okay, let's look at tetramethylbutane. Bute, meaning 4. Okay, tetramethyl. Now, tetramethyl means 4 methyl groups. Okay, so again, I'm going to start by drawing out my longest parent chain, which is bute, 4. Now, the reason that I do not have a location on tetramethylbutane is because I know that I cannot put a methyl group on my terminal carbons. Okay, so no carbon group can branch off of this guy here at the front or this guy here at the back. However, I do know that each of my center atoms or my center carbon atoms can contain a methyl group. So because there is only 4 possible locations and I have 4 possible methyl groups for those to happen, there's only 4 locations that they can be placed. To put numbers, to put 2233 tetramethylbutane would be a little bit redundant. So I don't need to do that. So I can simply put in that my methyl groups go here and here, giving me, oops, that's a little bit messy, tetramethylbutane. Again, if I'm to write this in a condensed structural formula, I would get CH3, and then I have tetramethyl, so I have 4 CH3s coming off my second and my third carbon, but again, I don't need to notate that. Again, take a look at my line diagram, butane. So I start 1, 2, 3, 4, and I have 1, 2, 3, 4. Okay, that is how I would draw tetramethylbutane. Okay, so hopefully you were able to jot down all of those examples and take some maybe a little bit tidier notes than some of mine. Obviously, you'll notice that, again, I start to lean towards drawing these line structures just because they're a lot faster and a lot easier to draw. Okay, sort of towards our end, we have cycloalkanes. Now, essentially in cycloalkanes, we have all carbons that are bonded to each other. So it's essentially taking a chain and wrapping it around so that we have the carbons at each terminal touching each other or bonded to each other. So cyclo means that it's in a circle per se, or they've all been joined together. Now notice we have a slightly different chemical formula. We have CnH2n, okay? So we've taken off that +2, meaning that if we have 3 carbons, we would have 6 hydrogens. So let's just take a look at that. If we look at cyclopropane, okay, let's take a look and see that it would be 1, 2, 3 carbons, and they are all bonded to each other. Now, because each carbon, again, likes to have 4 bonds, we would fill in each of these to have 2 hydrogens present. Okay, again, if I was to write my condensed structural formula, I would have CH2, CH2, and CH2 all bonded into each other. Okay, again, the reason why I love line diagrams so much is because for cyclopropane, our line diagram is quite simply a triangle. Okay, so if I look at cyclobutane, again, I would have C bonded to a C bonded to a C. Oh, this is going to get squishy. Oopsies. Here we go. That's our structural formula. Our condensed would be CH2, 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 and CH2 all bonded in a nice little square. And again, our line diagram is, in fact, a square. Okay, so you can see why, again, we like to draw more simple diagrams as we go through organic chemistry. Again, cycloalkanes, they're quite a bit less common than our branched alkanes or our unbranched alkanes. We generally don't see cycloalkanes unless they are about 6 carbons or greater. The reason being is our bond angles don't like to be pushed this tight together. So this angle, let me try and draw it here. This angle here that we have, that's forcing a bond angle that is beyond the natural bond angle that we usually have between our carbon-carbon bonds. Okay, same with butane. This bond angle is forcing it beyond what it's naturally supposed to be at. By the time we get to a cyclopentane, our bonds are pretty close. There's not a lot of force needed to add those in. And then once we get to a cyclohexane, again, those bond angles are a little bit more comfortable and we can have a little bit more rotation around those bonds. So like I said, they're less common. And they definitely are very less, not common at all unless we get up to that 6 carbon cycloalkane. So hopefully that wasn't too much on your plate to go through all of alkanes. Now, one thing you need to know is part of the reason why this lesson is so long is because this concept of naming alkanes is going to be carried through and consistent for every part of organic chemistry. So at this time, I would definitely take some time, go through some practice questions, either online or in a textbook, anything like that, to give yourself extra confidence before going on to the next portion of this unit. So, like I said, you might want to go back, rewind, take a look at extra practice questions, and good luck.